Welcome, everybody. My name is Sergei, and today we'll talk a bit about HSM security, about a little bug I found, and a bit about bug bounties. So a bit of a backstory for me while I looked at this. Well, obviously, it starts with being bored, and I got an email from HackerOne saying, hey, there is a program, maybe you want to participate. And there was a link to GitHub, and there was a firmware for the HSM. And this firmware was recently open sourced for some specific blockchain solution, which I know nothing about. There was also a public report, security assessment, also shared with all the findings, which were already patched by then, but was also nice to see. And once in a while, I enjoy those mostly blockchain-related projects because they often open source a lot of things, so I don't have to spend time reversing. You can go straight for the things. You can see like bug reports. You can see the assets they care about, and so on. And the last thing is, what I've seen from the project is that it's based on the Ledger Nano S hardware wallet. And I've done some research on it back in the day, and I still had a few devices laying around, so it was a perfect opportunity to try and find some bugs. So a little bit about HSMs, and there's a bit of overlap with different devices and some ambiguity to them. There is old school HSM devices, which you would have a dedicated component. It's a hardware security module. And you would have it for specific functionality. There is TPMs, which do a little bit of similar things, and secure elements like on your smartphone or your bank cards. All those devices, they are similar in a way that they used for cryptographic key generation, so they need to generate the keys in a secure manner. They store them also, hopefully, in a secure way, so you cannot easily read out the keys. And they're supposed to provide all the functionality to operate on those keys. So if you need to sign something, if you need to verify signatures, whatever you need these keys for, it should always stay within the device and never leave the HSM. And finally, unlike many other presentations today, we don't only care about remote attacks. These devices need to be tamper-resistant and sometimes tamper-evident. So if you have some attacker who has access to the device, they're supposed still to provide some level of security. So about PowHSM, what I initially figured out quite quickly. So it is some blockchain-related thing. I know nothing about blockchain parts, but I looked at some devices which I used for it, some hardware wallets in the past. So this one is based on Ledger. It is only software modified. So there is two main apps. There is UI and a designer app. And those are custom. All the rest is just stock Ledger device. And security-wise, it relies heavily on Ledger solution. But it uses a bit of an outdated firmware version, which we'll see later. So if you didn't see Ledger in the past, that's how it looks like. It's you have some desktop application. You don't trust your desktop to store keys, so you have a separate device. You connect it with USB. You enter the PIN on the device. And you have multiple applications you can see here for hardware wallet solution, and then you select one and use it for whatever blockchain purposes. For the HSM purpose, they changed this UI application, so it's not selecting different applets and not using it physically, but in an HSM setting. So how does it look inside? That's pretty much it. It is a very simple device. It has two main components. There is USB port, you have the buttons, and STM32 microcontroller, and ST secure element you can see here. And well, that's pretty much on a high level how it works. So you have the MCU. It has some code on it, a little bit of firmware. It interacts with the screen, so it shows you the data on the screen. It receives the data from the PC, the USB data, and it talks SPI to the secure element. And it receives the button clicks and also forwards everything to the secure element. So MCU is pretty much just a proxy. It's not supposed to do anything. It doesn't deal with keys or any other assets. It's just there to provide functionality for the secure element. And the secure element has the proprietary Ledger OS, and it supports multiple applications. And they are isolated, so there is a bit of security on that level as well. And in this case, we have this RSK UI app and RSK Signer app. So if we talk about attacker model, before we start with trying to find any bugs, that's how it looks like. So you only really trust the secure element. It is certified to some level. It's supposed to even protect you against physical attacks like fault injection, somebody shooting lasers at the chip. It should never let you get the keys out. And everything around it is not really trusted on the device. Even the MCU, which it talks to over SPI, it's not really in the trusted components. And of course, you don't trust data you receive over USB from your PC at all, because that can be easily compromised. Just a little side note here. So we'll see it later, but there is, on the back side, there's a little JTAG. If you know hardware, you know this is a debug port. And it is for the STM32, so it's not for the secure element. But the ST chip is so untrusted, the STM32, you can even run and debug it fully out of the box. So I started looking at the code a little bit. It's all on GitHub, as I mentioned. So, and it's very simple. It's just some C code. There is a main dispatcher. It receives the commands. It parses them and sends the data back. And you have some obvious things like you can sign data. You can ask the device to give you the public key, and it will easily do that. There is no command to give private key, because obviously private key never leaves the device. And there is some blockchain-related things. So there is a bit of parsing of transactions and other things. But we'll see later on. And of course, always nice to look at the prior research. So there's this report published, and it's also linked and shared by the vendor, which is nice to see for transparency and just makes it easier to do research. Of course, all of them were fixed, so it's not really important, and there is not too many issues found originally. So what did I do? I've done the same. So I got the code, started to look at the obvious things. So you care about PIN verification. You make sure that you check it before you do any transactions. You make sure that the authentication state is what you expect. So you cannot sign before you authenticate. Like, look at the transaction parsing. So I've done quite a bit of fuzzing on it, but not really gave me anything. Looked at the transaction states. There's quite a bit of transaction-related things. But since I don't really have background in whatever blockchain purpose it is, I only could look, obviously, at the memory bugs and like obvious things, not at the deep logical blockchain-related things. And at this state, obviously, I was getting a bit desperate, didn't find, there was a lot of small things, but nothing really I would care about reporting. Being in a desperate enough position, I looked at the decompiler, because sometimes compiler can add some optimizations which change the logic, especially on the low level of things. So, and when I dropped it into the decompiler, I've seen the strings which I didn't really expect to see. You can see here on the right. It's the USB-related functionality. And it is strange, because all the USB stuff is supposed to be done by MCU. And the data you receive from the MCU is over SPI line. So there is no obvious reason why you would have USB packets there. And I thought maybe it's some kind of artifact which is not being used. And right there, so it's the way it receives data from the MCU is there is USB protocol over this SPI line. And that's really strange for no known to me reason, to be honest. Maybe there was some SDK released by ST manufacturer for the secure element, which had this, and they used it. Or maybe their initial idea was to use only secure element without MCU, so it had already USB parsing. But from this moment on, I probably spent 10 minutes, and that was the bug. So you have the SPI buffer, which is fully controlled by your untrusted environment. And you get the index. It's 128 possible indexes, and it's whatever you provide. And you get the byte, and you write to the global data. So, and the global buffer, it's USB endpoint transfer length. There is 8 endpoints for USB for the signer app, and there is 2 for the UI app. And this bug is on both the UI and the signer side of things, so it's because it's part of the SDK. And so what we can do is obviously write out of bounds 128 bytes. So this data is in RAM, and all we need to figure out is how to trigger this bug now and what to corrupt then to get the keys out. So to trigger the bug, you could possibly think about remote scenario, and that's what I spent some time on as well. So ideally, you would like to remotely compromise the MCU, get code execution there, and then you can send arbitrary SPI data to the secure element, which wasn't really successful. So I had to resort to another attack path. And luckily, these high-end security devices, like HSMs, they have to protect against physical attackers. So you can see here the device. And this JTAG port, which was on the back, is connected with these tiny wires to the ST debugger, which you can buy for a few bucks. And you can use standard software. And you have full control on code execution on the STM32 with that. So any attacker walking into a device, connecting the debugger, can run arbitrary code and can send arbitrary SPI data. It's not even necessarily needed because you can also tap on the line itself if you want to do more hardware stuff. So the second thing is what to corrupt, and that was also, there is a few things there. Maybe there is better targets. Just for the POC, there is obviously a callback. So transaction parsing for the blockchain purposes will have some callbacks in the parsing. You will send a chunk of data. It will call a callback and parse it. And now we can fully corrupt this pointer. So the idea is we grab the pointer, point to a fake callback structure, which has our pointers, and we have full control of the PC there. And that was very easy. So we can like jump to a random piece of code within the app. As I mentioned, there is no return private key function, unfortunately, because that would just give us the private key. So we need to figure out a little bit. So these devices not really have a lot of mitigations. Unlike browsers or smartphones, there is barely few. So this one has the MPU configured because this is an app which runs within the OS. And unfortunately, the RAM is not executable. And the RAM is where our all data is. So ideally, we would like to just jump to the shellcode and be done with it. But there are still a few things which are relevant for us. And this comes from my previous research in the past. So there is some persistent data. An app might want to save to flash. When you run, you change the state, and you save it to flash to use it later between reboots. And this persistent data resides in the same flash region as your code. And there is the same MPU permission to this data. So unlike most of your data in RAM, you cannot write and execute this data. Data in flash, you can write through the syscall, not directly, but eventually it will have your data, and if you jump to it, it will execute it. There is the second nice thing related to this, which we'll use later, is that the NVM write syscall does not forbid you from overwriting your own code. And in general, maybe you would think it's not a big deal, but for this solution, you only allowed to load signed application. You check the signature first, then you do sort of attestation on every boot. So you don't really want to allow applications to modify themselves and get persistence on the app as well. So that's probably undesired behavior. Maybe it's also the moment to mention all of those things were already fixed by Ledger some time ago, but there was still an issue here. So some of them I rediscovered again, and some of them were clearly fixed before. So how can we use that path? There is probably blockchain state structure, and it has quite a few fields. Most of them are hashes, unfortunately. So it's some blockchain data coming in. You will store a hash of next blocks or last process block and so on. And those are stored persistently in Flash. And you can see some of them are, in fact, updated when you process your transactions. So at this point, it was quite annoying because you would have to figure out the whole proper blockchain flow of things to corrupt one of those blocks. I found the easiest one, just for the POC purposes. It is the compile time parameter, just the initial value. So we will not modify the application, but we set the initial value to our shellcode, just to make it easy for us to jump and show that it can be done. So now we have all the pieces quite easily. We have our shellcode. It's not a lot, it's 32 bytes, but we execute in thumb mode in ARM. So we can have up to 16 different instructions and maybe some data if we need to. And after trying to figure out, I chose the way of, we point the source to our SPI buffer because we control it with our shellcode. We point the destination to somewhere within our app. And there is no randomization, ASLR, all the offsets are fixed, so we don't need to worry about that. And we call the NVM write syscall, which allows us to write our code. So eventually, we'll just copy SPI data to whatever is in Flash and corrupt anything of the existing code. So what will we corrupt now? You probably can try to read a little bit what it says. So this is the command says get public key. And what it does, it calls a syscall, tells the OS, give me the root private key secret, because it's not stored in the app, it's stored in the OS for security reasons. It initializes the key, wipes the private key, so it's not in memory anymore to make sure that it's never leaked. Generates private key, a public key from the private key, wipes the key entirely as well, and then only then copies the public key. But since now we can corrupt the code, we just nop all the parts until we return the data, make sure we return the right number of bytes, and that our register doesn't contain the public key pointer, but the private key pointer. And that is pretty much it. So for the POC I shared with the vendor, you can see we send the get public key command and get 65 bytes back. It's the compressed public key. And do our corruptions and point to the fake structure, modify the callbacks, smash the data in Flash with our corrupted, with NOPs and changes to the get public key command. And when we call it again with the same command, we get the private key out instead of the public. So that was it. That was for the proof of concept part, just to show and report to the vendor. And these bugs were fixed after that and resolved, mostly by just porting the patches which were missing from the Ledger SDK. And that goes to the conclusions. I thought about what kind of conclusions to mention here. And there is obvious things, of course, which are relevant for many devices. There is not a lot of mitigations. On even high-end, low-level devices, mitigations are not really there. There is unnecessary complexity. It's still a mystery to me why there is USB over SPI implemented there. But if it's there, I will be happy to exploit it. And there is a patch propagation issue, which is common for so many different products, and it's probably going to be there for a while with us. But instead of conclusions, I will do a little bit of modern-day archaeology. I showed you, I put a code in the decompiler. That's how I found the bug. I could go back to GitHub and just find it, source code, obviously, but I was already too excited. And you can see this is the original Ledger code before it was fixed. And just before this bug, it says, save just in case it is needed. And it was needed for this presentation.